Hello, it's Keith from Kinvert, and we're going to do another applied math example. We're going to be going over composite functions, right? A function within a function. I'm not here to teach you the topic, but rather to show you an example. So let's say that we are dropping a ball. All right, so we're going to drop a ball. It's going to be falling down because of gravity, and the acceleration due to gravity, the acceleration for gravity is going to be 9.81 meters per second squared. This is the number we're looking at. This is the acceleration that's happening. So the velocity is a function of time, and that is going to be at plus v0. So let's just say v0 is the initial velocity when we drop the ball. Well, that's just going to equal 0, because when we're letting go of the ball, at first the ball is staying still. So the velocity is going to equal the acceleration times time. So the longer time goes, the more the ball is accelerated, the faster the ball is going, right? The acceleration itself is constant. But what we also want to find is the kinetic energy of the ball. So let's give the ball a mass of 1 kilogram for simple math. And the kinetic energy, we'll call it K, is half mv squared. Does that make sense? So now K is a function of the velocity, but the velocity is a function of time. So hopefully that makes sense. So let's start looking at this. If that's v of t equals at, so now we're going to start putting in, I'm not going to put in a negative. We're not going with the real reference frame here, I guess. So we're just going to call this 9.81 t. So that is the function that is going to describe the velocity. So at 0 seconds, it's 0, which means, we're still holding the ball. At 1 second, the ball is going to be falling at 9.81 meters per second. That is our first function. But to find the kinetic energy, we need to take the composite function with that, right? So we've got, so let's write this out further. Switch colors. So the kinetic energy is half times the mass, which in this case is 1. So let's just write it out further, times v, which is a function of time, squared. All right? And so we can write K equals, since the m is going to cancel because it's 1, half times basically v of t. So let's swap in, what is v of t? Well, it equals this. So now we can put in 9.81 t. Now let's find what is the speed of the ball, what is the kinetic energy of the ball? Kinetic energy of the ball at 0 seconds. What is it? Well, we would punch in half times 9.81 times 0. So the kinetic energy there, the kinetic energy at 0 seconds is 0. What's the kinetic energy at 1 second? Okay, so we're going to have half times 9.81 times 1. So it is going to be, what, 4.95? 4.95, and if we look at the kinetic energy at 2 seconds, that is going to be, well, it's going to cancel out this half, so it's just 9.81. So composite functions, they might look like they don't have a use, but if you're finding the velocity, and this is very normal to find the velocity with respect to time, particularly dropping an object, okay? And if you want to find the kinetic energy, which is, it matters, you need to know how much energy is in that system. Let's SpaceX landing rockets. They need to know the velocity of that rocket. They need to know the energy level of that rocket so that they can start calculating when do they need to turn on the engines, how much thrust do they need to properly land that rocket. The kinetic energy is a function of the velocity, and the velocity is a function of time. And we now have a composite function. So I hope that made sense. Again, this wasn't meant to show you in-depth examples of how to calculate them and what to do. This is meant to show you, you're going to be looking at this and wondering, hey, when am I going to use this in real life? Well, here is one example of among many of when you would actually use a composite function. So I hope this was helpful. This is Keith from Kinvert, and if you enjoyed this, check out the link below. We've got a lot more applied math examples like this one, and we'll see you guys later. Thanks a lot. Bye.